Hello, my name is Erdem Topsakal. I'm the editor-in-chief of IEEE Antennas and Propagation Digital Communications. We are here in Ann Arbor, Michigan today. Welcome to another episode of Legends of Electromagnetics. We are here visiting Professor Kamal Sarabandi. Thank you so much for having us.
Absolutely, Erdem. Thank you for coming after so many years to Michigan. We welcome you to Ann Arbor again, as it is open always for you to come here.
Thank you so much. So I'd like to start with your background. How did you get into engineering and how did you get into academia?
That's an interesting question, Erdem. This goes back to my childhood. When I was fourth grade, I remember I was in my friend's house. He had an uncle. He was an electrical engineer. So we were, playing, and he comes in, and I don't remember exactly what it was, but he asked us one question. He said, if I turn this switch on, how long does it take for the light to come on? And we said immediately. He says, no, there is a delay. And ever since I wanted to know what that delay was for. So, it really interested me in the field of electrical engineering, believe it or not, at age 11 or so. So ever since I've been in the pursuit of electrons, trying to find out where they go, how they go, what are they influenced by. So I knew from then that I wanted to get to engineering. I knew that I wanted to get to electrical engineering. So I attended the school in Tehran, Iran. In 1969, I entered this high school. It was a high school for students with talent in math and physics. So it was like a, competition to get to that high school. They would pick up students from top of the classes and then people who were very good in math. And I got in there, and I remember the first math exam I took, I was almost in the middle of the class. It was a shock for me because there were so many good students. But, little by little, I got a hold of it. And then once I was graduating from high school, I picked electrical engineering at Sharif. I entered there, and then it started doing electrical engineering. And among electrical engineering, I was fascinated by electromagnetics because it required both physics and math as a prerequisite to do stuff like that. And I've ever since been doing that. I graduated from that school with 1 year delay due to revolution in Iran, 1980. And I wanted to come to the United States for a PhD, but the war started. And then it delayed me for about 3 or 4 years. Nevertheless, after finishing my military service during war in Iran, I came to Michigan. And I was fortunate enough to enter a program that was extremely good in electromagnetics. And it had so many good professors doing electromagnetics. Professor Ulaby was my advisor at the time. He just arrived at the same time I arrived in Ann Arbor, Michigan. He was coming from Kansas. His field of research was interesting, radar remote sensing of environment. And I thought, wow, what can be better than that? I was doing a non-military application of radar for something that affects every human's life on this planet. Radar remote sensing was its at infancy at the time. There were sensors people were using. People started to look at how to interpret what the radar reflectance off of the ground is going to be. And, I started doing that. So I was doing a lot of fundamental work that is very much related to antennas and propagation, even though this was remote sensing. Scattering problems are, basically were very hot at my time. Doing analytical work was very important. At the time, if you remember, computational electromagnetic was getting quite a bit of traction, right? And using all these techniques for problems like being able to electromagnetically solve backscatter from terrestrial targets that are random in nature, they're very complex, and be able to do that. I think my thesis at the time was among the very first to look at this problem from completely mathematical and in a sense electromagnetic way by trying to calculate the scattering from leaves, branches, tree structures, this interaction of those with each other, interaction of those with rough surfaces, electromagnetic scattering from rough surfaces, effects of all of these things, and be able, towards the end of my PhD, to put all these pieces together to have a comprehensive model to calculate polarimetric backscatter from such terrestrial target, and then using those as a forward model. For the inverse model, the big problem in remote sensing at the time was estimating, how much carbon dioxide that is produced through human activity and released into the atmosphere, greenhouse gas, affects, the global warming. At the time there were believers and there were deniers. People were saying that, the Earth has the ability to fix itself. No matter how much carbon dioxide we generate, vegetation or biota in ocean would be able to take them in, and then we would maintain balance. So the big question was, can we measure how much biomass gets generated every year, how much biomass we lose? And we were resorting to imaging radars and these models to do that. So that was basically, from my childhood to undergrad to graduate school. I remember also at the time when I finished, my wife was still here at dental school, and she had another 2 years to go, and Professor Ulaby came and asked me if I wanted to stay for 2 years as a research scientist while she was getting to finish her studies. And, I really was enjoying what I was doing here, and I said yes, and I stayed there. By the time she was graduating, and they offered me a faculty position to stay in Ann Arbor, and I really liked it, ever since being here. Since 1984, it's almost 40 years, 39 years now that I've been in Ann Arbor. So I really enjoyed the school, the facilities we have, the environment we have, the type of a student we get. Really top-notch students, that these are the things that have kept me in Michigan and kept me on my work here.
Great. So, just to follow up on that, of course, you've been in the academia so many years, and being a faculty member requires, doing research, writing papers, bringing in grants and all that. So I have some of your work in the past. If you can, go start from
one of them,
and
sure.
gradually go.
Sure. Let me tell you a little bit about my philosophy of doing research. I think it's very important that, like any business that you have a wide portfolio. You diversify what you do, right? Also curiosity, which is the source of, what keeps us going, what makes us interested in our research, right? There is that level of curiosity in you that makes you want to know everything, right? So, from the onset, when I became a faculty, I promised myself that every 5 years I open up a new field of research, do something else, do something new. 5 years of, intense research in something would eventually bring in result that is new and it's useful and things like that. And not that you have to abandon them, but you add them to your portfolio. You let these things going forward. So this has been the philosophy of my career from the onset. That, okay, I did this, I can't continue with that research, but, I can recruit a student, I develop an idea on something and start doing that. In year 2000, very early on, there was a DARPA program on metamaterial that metamaterial was just getting, started. The concepts were being developed. I thought this would be something that we could do. And we started looking into use of this metamaterial in doing novel things, in antenna engineering, in scattering problems, in all sorts of different gadgets and tools and things like that you want to do. So at the time, we focused a lot on engineering effective dielectric, not necessarily negative dielectric. Most of the community metamaterial, they were focusing on double negative, dielectric and permeability to get perfect lens, but my research went on a different path to come up with anisotropic material, to come up with effective dielectric that we could make Bloomberg lenses, for example, and things like that. One of the examples that I had a collaboration with one of our faculty members in material science. 3D printing at the time did not exist, but this is them, as you can see. These are basically dielectric resonators that are 3D printed. And the material used here is not plastic, but it's ceramic, it's alumina. Alumina, as you know, is basically porcelain, right? And it's very rigid, it's very hard, and it's very difficult to do 3D printing with that. So with collaboration that we had with my colleague here in material science, he had this technique of using ceramic stereolithography. Basically, a monomer, you create a slurry like a mud, right? And then you would come with a laser. Laser would hit that monomer, make it a polymer, and it solidifies. And therefore, you can capture these very small, nano-sized particles of aluminum oxide into a shape. So these things would come and dry. There was an elevator would go down, and it would only come back so much to allow for the next layer to be written on. So that's how we generated 3D printing of this type of material. There is pictures of Bloomberg lenses that we made with that. But this is one specific example of making a dielectric resonator array using a 3D printing. This was in early 2000. That was one of the early examples of using 3D printing. And why do we use alumina? Is because of loss. Alumina is known to have very low loss factor, right? And then that's why we were very much interested to get into Ka band, Ku band type of array structures. We continued this type of research in developing other types of things. This is, again, the first antenna that is designed by 3D printing metal, right? So this came out in 2015, 2016. This structure is very complex. It has complete three-dimensional. Actually, it's also the first very wideband full duplex antenna system. What you're holding operates between 7 to 14 gigahertz of bandwidth, right? And then isolation between the two ports of the antenna is about 60 to 70 dB. So we could use this as elements of cell phone towers. We wanted it to expand the use of a spectrum. If you ask me what is the most expensive commodity, it's a spectrum. A spectrum is by far the most expensive thing that we have because there is very limited, amount of bandwidth that is available. Nature has created only so much, a frequency band in which you can use electromagnetic. And in this case, for communications, you need to operate in microwave range, right? So in microwave range, you can penetrate through walls and buildings, and that allows wireless.
What's the material?
The material used in here is aluminum.
Aluminum. Okay.
Yes. Yeah.
It's pretty lightweight.
It's very lightweight and it's very complex. Actually, you have, we cannot open this, but there is suspended air strip lines that feeds the element. So absolutely no loss. Aperture efficiency of these antennas is very, very close to full, almost 95% or so.
Great.
So this is another, aspect. And I was, as I was telling you, another type of thing that we did in the area of metamaterials, where metasurfaces. Our group was, again, among the first to introduce these type of surfaces. We initially worked with a postdoc I had on reactive impedance surfaces for antenna miniaturization. During the years of 2000, antenna miniaturizations for cell phones, and we did a lot of work on that. There are a lot of papers on cell phones, size antennas that we developed some of them based on metamaterial. One technique for antenna miniaturization, especially for use at very low frequency, was the use of these reactive impedance surfaces. We demonstrated that if you use a inductive surface, you can tune a sub-wavelength, for example, monopole or a patch antenna on that thing and shrink the size significantly. The other class of these metasurfaces that we came up with was the use of sub-wavelength structures. Like what you see here is a reflect array that was built in early 2010. I guess this was maybe 2012, where we are using these sub-wavelength metallic structures. This loop behaves, for example, like an inductor, which is this piece, and you have this base for that. To the next one, it acts like a capacitor. So you have spatial circuit elements in your, let's say, surface. So as electromagnetic wave impinges upon this, it sees a filter. Once it sees a filter, as the signal passes through, there is a phase shift. We use that phase shift, for example, for lensing, or in this case, reflect array. One very important feature of these miniaturized element frequency selective surfaces is the fact that they do not have harmonics, because each element is like lambda over 10. For the harmonic to show up, you need to have multiples of wavelengths, right? So this acts very broadband, right? You don't have spurious responses because of this. The other thing is that since they are sub-wavelengths, they act locally. Like ordinary frequency selective surfaces, you need to have many elements to be present in order to see the effect of them. But since these are all working on the TEM electromagnetic, they act locally, so we can have, completely dispersed. Instead of being just purely periodic, they are very, very diverse elements, and we can do phase shifting, we can do lensing and stuff like that. Actually, we have just recently completed a reflectionless lens at 240 gigahertz using macro machining technique, and in clean rooms we were able to make a lens based on this same concept. In 2008, one of the other things, I was telling you, finding another way of doing research or doing other types of research was to see how we could come and help robotics. In robotics, a lot of things have been solved, a lot of techniques have been developed. But one major problem with robotics is the size, weight, and power consumption, right? This is critical for the operation of any robot that wants to have a meaningful or purposeful function. So in year 2006, 2007, there was a call by the Army Research Lab to develop 3 centers, simultaneous collaborative centers, one on microelectronics, the other one on micromechanics, and the third one on autonomy, basically signal processing, tools, and things like that. So I led writing a proposal on that. This was a major program, about $25 million worth of contract, and we were fortunate enough to win that contract. And in there, we formed a group of about 12, 15 faculty members, mostly from Michigan, to lead an effort in trying to make communication more reliable, to make the power consumptions of electronically by an order of magnitude smaller, to make things that would perform functional while we were reducing the weight, size, and power. One example I'm going to show you, for these robots to operate in any weather condition, you need them to be able to see. So you can use cameras, of course, but cameras do not perform in dust, smoke, and poor weather condition. You also, at night, you want to operate. So we thought of developing a radar system at 240 gigahertz that weighs only 5 grams, and it's beam steerable. So this is a radar system, the antenna portion of that is made up of 1,200 patch elements on these things that is far smaller. It's quarter size of your credit card, actually, right? And it weighs less than 5 grams. You can put it on these quad rotors, you can put it on flappers, and this can scan the beam in one direction. It has a beam width of about 2 degrees, and you can use it for collision avoidance and mapping interior of the building. And we demonstrated that back in 2016-17 that operated, and now we are thinking about using this same technology to transition these to automotive industry. Part of the problem with silicon macro machining is that they're not scalable. You cannot lower the cost. So we are working on that aspect to see how we could maintain tolerances like this that we can get with macro machining and yet be able to reduce the price of that. Another technique that we use for communication, for example, we had these small crawlers, we had these flyers. These were all supposed to be totally autonomous. You need to have communications among them, right? How do you I don't have enough power, right, on my small robot. So we developed these radios that were very low in power, but instead of being victim to your communication channel, we ended up designing these small repeaters. These are radio repeaters, and this is a bigger version of it. We have a sub-wavelength radio repeater that operates in a full duplex environment. You have one transmitter and one receiver antenna, but isolation between this transmitter and receiver is in excess of 70 dB. Therefore, if we can receive a signal by this macro repeater, amplified by a factor of 50 or 60 and re-radiate, you change the communication channel, right? Then, so for example, as the robot goes around the corner, they can drop one of these and then continue. And therefore, you can have like these breadcrumbs for the path of communication between your transmitter and intended receiver. So this was another innovation that we had. We had also developed a wide range of imaging systems, the true wall imaging system based on fully robotic stuff. If you have time, I can take you to the lab. I'll show you also the robots we are making for subsurface sensing and things like that based on the same concept that you can enable a fully multi-static imaging radar on few ground robots, for example, to see through walls and map what is on the other side, detect movers on the other sides and things like that. So a large number of small antennas. One of the major issues, for example, you see these types of antenna can transmit purely vertical polarization. Why is that important? In wave propagation, that's goes back to my early work of developing models for wave propagation for communication. So we have done a lot of work to realize the effect of polarization. Actually, when you're transmitting horizontal polarization and you're operating near ground, the reflection off of the ground totally cancels the direct signal, and therefore the signal drops significantly. Whereas if you transmit vertical polarization, the difference between horizontal and vertical polarization can be in excess of 50, 60 dB. So you have hugely better path loss when you're using vertical polarization. But vertical polarization requires an antenna that's sticking up, right? If a crawler wants to go under the door, that antenna doesn't allow it to do. So we spent a lot of time developing antennas that are very low profile. We have the world record of developing antennas that can transmit purely vertical polarization while having a very, very small vertical height. Okay, so that is one of the things that we have done in this one. So we can go on and on and on these, but I think at least I answered some of your questions.
Yes, no, I think you answered mainly the question, and clearly, I mean, in so many years of work, you have done many things, and as you said, that changing things every 5 years, I guess, it really, help your research, looking into different things and contributing in different ways.
Yes.
So moving on to my next question, I would like to talk a little bit about the awards that you have received over the years, and we see two of them here. And also, I see, the National Academy of Engineering, membership plaque back there. So can you tell us a little bit about, how these awards, came about and,
Yes. No. Awards are usually provided based on the outcomes. And I have been fortunate to be recognized for some of the works I have done. Of course, we don't necessarily want to go after awards.
Yeah.
That doesn't make any sense. But after a while, as I mentioned, if you maintain a high quality of research, society would recognize that. People would recognize some of your former students. Sometimes they nominate you, you don't even know, right? And some of these things came about. And as I said, I feel very fortunate about being able to receive some of these quite prestigious awards and recognitions throughout my career. Most recently, induction to the National Academy of Engineering is totally an honor for me. To be part of this very elite group of people who have had major impact, not only in academia, but also in industry. And all of these things are done eventually as a payback to the society that supports us. We researchers are at the end of the chain of money path, right? Recognition of the society for spending money, trusting people that we do research for the benefit of the society and the impact. Actually, this is something that I would like to emphasize, that one of the things that I choose when I write a proposal or when I want to do a problem is I assess, where would the impact of this be? Is that going to help an industry? Is that going to lead to something that would affect people's health? Things like that. We didn't get a chance to go and finish some of the things. One thing that I started 5 years ago was bioelectromagnetics, which I now really love to continue doing. Of course, we are age limited, but the fun is there. I believe everything is mediated by electricity. Electrical engineering is one of the most important field of engineering. Our body, it's all biology, but everything in our body is mediated by electricity. The entire chemistry is electricity, right? So this is an area that has not been looked upon by electrical engineers in any significant way. 5 years ago, there was a program by DARPA. They wanted to know how cells would communicate. This DARPA program, when I read the announcement, I said, okay, this is something that I would like to be part of, right? So talked to colleagues here, and we put a proposal together. And again, we were very fortunate enough to get that. Also, there was a very nice program manager, Mike Fidi, was running this. Very nice gentleman, very good thought process and thinking about even introducing this problem, whether there are electricity involved in communication, right, among cells. And so we looked, I'm going to make this story very short. We developed this model based on mechanical antennas. There was another DARPA program that I did some work on that. So and that was fresh in my mind. And I said, how could a single cell have a radio transmitter and a radio receiver built in a single cell, right? That's fascinating, right? So we found out that there are actually mechanisms for that based on mechanical antennas. These structures attached to cells are so small that when they go to vibration, they fall into hundreds of megahertz or gigahertz range. And then we looked at natural resonant frequencies of these, and then we postulated that, yeah, there is a radio transmitter. Yes, there is a radio receiver. And eventually, for about 3 years, we developed the most sensitive receivers to be able to listen to bacteria radiating electromagnetic wave. We just published a paper. For the first time, we demonstrated the presence of electromagnetic radiation off of individual cells this paper is just it came out, and we are very proud of that. And I think this is one of those things that would have a major impact, because imagine instead of taking antibiotics, you can go sit in a place and somebody would come and jam these bacteria inside your body to disturb, or disrupt their communication and things like that. Or for cancer cells and things like that. This is far off, but this is an initial step, I think. This is something that had not been demonstrated anywhere. But it comes because of the fact that we know antennas, because of the fact that we know electromagnetics, because we are interested in seeing and discovering different aspects of how nature works, right? The center I had was actually called this is that brochure for that center. Center, we call it Objective Microelectronics and Biomimetic Advanced Technology. But why biomimetics was part of this center? Because we wanted it to learn from what nature has developed. Yeah. And we learned so much, and so many of these ideas that we actually ended up using was inspired by what we saw in creatures. So, okay, I think I answered that question as well, but lengthy answer. Sorry about that.
No, it's okay. You're clearly very excited about all the research, which is exciting to me as well. As you know, my research area is also
absolutely, yes.
So it's dear to my heart. I want to, shift gears to students.
Yes.
Large part of the academia is basically students. So we wouldn't be here if it wasn't for the students. So I see here a book. Which is a textbook.
Yes.
So it's the Foundations of Applied Electromagnetics.
Yes.
So can you tell us a little bit about this book?
Sure. So during COVID years, of course, I've been teaching the first graduate level course in electromagnetics. And I've been using my own notes for many years, and you always have in the back of your mind that you're going to write your text, but doing research and other responsibility, this gets delayed and delayed and delayed. COVID was very bad and disastrous for the society, but it had also some positive aspect, and this book is one of those that I was able to concentrate actually some of my time, because I wasn't traveling. I had more time to stay at home, and my colleague and former advisor Fawwaz always has these very nice ideas, and he wanted it to have a major impact on graduate studies, or also undergrad, not just necessarily graduate school, but higher education. How do we lower the cost of higher education? How do we make it more fair, equitable? How do we make things more affordable to people? So he started an initiation of free textbooks. And he said to me, Kamal, do you have any ideas, that you could also contribute to this, And I felt, as I said, owing to the society, owing to my community, I said, okay, this is something that I can leave behind. This is something that is close to my heart, and I can put a lot of effort into this and offer it for free to all students and researchers worldwide. So I wrote this book. It took me about a year to finish it, spent close to 3,000 hours of work on this textbook. It's a modern version of applied electromagnetics that I teach, and inspired by a lot of things that I do from my research. Things that I wanted to know when I was a graduate student. I wish, these things were somewhere I could find. So I started writing this book, and we finished it in November, and the book came out, and I put it online for free. Anybody who wants to take it, they could download it, take it. We are also using University of Michigan Publishing. We have an agreement with them so that they are offering this book basically at the cost of printing and shipping.
Great.
So you can buy almost 620-page book for $75. The whole thing is colored.
Oh, nice.
All the figures are colored and everything. So you get a color book, hard copy for $75 if you want. Otherwise, it's free to download it. And Adam, you can't believe this. In 3 months, 4,000 copies of the book was downloaded.
Oh, nice.
How could you have? I mean, if I were to sell this, probably I've been selling these 200 copies by now, right? So I think this lowers the bar for students who want. Maybe somebody gets excited about our field of research. I felt I wanted it to make this more accessible and make it easier for people to get to.
Great. Well, just to tie up to this is that I want to talk a little bit about Antennas and Propagation Society.
Yes.
You have been a part of APS for quite a number of years right now. You're already serving the AFCOM. So can you tell us a little bit about your connection with APS and how APS affected you as a researcher? And also, do you have any recommendations for the students coming into APS?
Absolutely. Students are, I guess, the most important, you mentioned it, the most important components of any educational system, professional societies. These are the people who would be carrying on the torch from us to the next generation. So any investment that we can make to students is extremely important. For me, you mentioned, how I got involved. When I came to Michigan, there was a student chapter, from very early on. My membership goes back to 1984, the year I arrived here. I wanted it to be part of that professional society, societies of volunteer organizations, or in general, they are giving so much to that profession. And I felt this is, very important to be part of it, So I was involved with that from very early on. I've been member of 3 societies actually, without any stoppage. One was Antennas and Propagation, Geoscience and Remote Sensing, Microwave Theory and Techniques. These were the 3 societies that had everything I wanted it to know about electromagnetics and high frequency stuff. And, I've been a member of that ever since. Maintaining societies like that is extremely important for our field of research. As I mentioned, electricity, electrical engineering, and in particular electromagnetic. A lot of people think, electromagnetic is an old field. That is not the case. I gave you just one example about biology where this thing can be used, right? Until we find ways of transferring power and information, electromagnetic is going to be relevant. Antennas, wave propagations, microwave circuits, all of these things, the tools that we make with these things, it's incredible, right? Their implications on our everyday life is humongous. Students nowadays have a cell phone, they take it and they use it. They don't know how much of that is really based on electromagnetic and our knowledge of how wave propagates and how antenna works, how RF circuits are designed and things like that. So it is very important, we need to make sure they understand the importance of that, all right? Physical sciences are not going to go away. You invest as a student any time doing learning about physical sciences, that is a constant. That does not change. It's not like a software tool that changes from this year to next year to next year to next year. this is something that you can build your career upon. It's a solid foundation. And it would help you going, and you would have enjoyment along the way, right? I sometimes tell this to my story. If somebody give me $1 million, I'll be happy for a month, but then, it becomes ordinary, right? But whenever I think back about any of my discoveries or something that I was able to solve, a problem that I was to solve, even if it is 25 years ago, still when I recall that, so many dopamines come out and makes me happy, right? That is unmeasurable, right? These are the things that makes the quality of the life.
Great. Thank you. My next question is about recruiting, underrepresented minorities. As you know, that it's extremely difficult, and in the past 40 years of your career in the academia, specifically, recruiting minorities, especially women, to electrical engineering.
Right.
So why do you think, we have less women than men, in electrical engineering? And what are the things that we can do to promote electrical engineering to more women, specifically antennas and propagation and microwaves and electromagnetics?
Right. No, this is a very fundamental and very important question, and I'm happy that you're asking me this, because I have been thinking about it. As you said, we try to attract a lot of minorities, specifically as regards to gender, to engineering, electrical engineering, to show them that this is really a very fun area and something that actually a lot of, independent of your gender, I think you can really enjoy these fields. But why is it that we don't have as many students interested in our field? Some of it is historical, and we are trying to the environment, how they would perceive the environment. When they are coming, let's say, to a lab where 90% of the students are male, there is a level of intimidation that you don't feel you are part of that, or you could basically excel in an environment like that. And that is an issue, right? So we are trying to make sure that, address the environment issue for students who are coming, no matter what background you have. But once you enter a place where you don't see many of you there, it's sort of intimidating. So we have to solve that we have to remove that barrier. But also there are some fundamental issues. And I can give you one example, all right? One example, in year 2000, I was invited to go back to Sharif to give a lecture. I went to the lecture hall, and like 200 students in the audience, and many female students, in fact, more than male. So I'm being naive. From my time, maybe in electrical engineering, out of in my class of 120, there were like 2 female students as my classmates. But here I see more than 50% of the students are female. So I asked, are you all engineers, electrical engineers? They all say yes. So, oh my God, if they can do it in Iran, why can't we do it in US? What is the difference then? It goes back to high school.
Of course.
It goes back to high school. Anything related to STEM. Our neurons connectivity takes place when you are a teenager, when you are transitioning from childhood to adulthood. This is so critical at that juncture to instill these ideas at that time. We really need to work, counselors at high school, funds maybe, encouragement, getting female students at that time to define for them engineering as a path, electrical engineering as a path. I think that is where we are missing. We come to graduate school and say, oh, how come I can't find a female graduate student? How come I cannot find minorities? These are all happening at high school. We really need, the society needs to pay a lot of attention to what is going on in our high schools and try to fix this problem right there and then. And you will see, we will have more than 50-60% of excellent students who right now end up doing other things. But if we want to recruit them, we need, I go sometimes, I still have a son in high school. I go to high school and talk to the counselor, So this is the time to encourage. Actually, we need to have the best paid people should be students, they should be teachers in high school. I mean, the society doesn't pay too much attention to teachers at primary and secondary level. And this is something that the society really have to change.
I totally agree with you. Coming from Turkey myself, actually we have more female students in the electrical engineering than what we have in the United States. I totally agree. So, and the high school
is the
we
key.
need to invest in high school is the key. My last question
Yes.
of the day, last but not least, is about work-life balance.
Oh,
right? You work
right.
so hard, day and night, and write these grants and
Yes.
do this wonderful research, write books, help students,
Yeah.
graduate them. Of course, you need to do something to unwind and, so what are the things that you do? What are your hobbies that nobody knows about?
Okay, yeah. So hobbies and things like that. So I work around home. I fix things. So I really like doing those type of things. But besides that, I would like to spend times with friends. One thing that human is a social animal, right? We have to have friends for our life to be meaningful. Trying to find friends, Okay, I have to go back a little bit, tell you something, Erdem. Have you ever felt that as we age, time goes faster,
Of course.
right? So this bothered me a lot. I said, why is it like that? And it is the true sense. I experienced it. I ask everybody else at my age or even before, they feel the same way. And it occurred to me that the passage of time, the sense of passage of time is proportional to how much new memory you make. Right? If I'm coming to my office, see the same setting every day, I don't make any memory. Right? So I said, what happened to the day? Nothing. Yeah. Right? You go home, you come, you go home, you come, and then nothing. There is nothing. Right? So once I realized that, I said, okay, I need to change this. I need to be able to make memories, making friends. You can talk about some of these things that you experience with a new friend, and it's new again, right? And you really enjoy, you make memory by making friends. You make memory by changing your environment. When I come to work every day, I don't take the same path. I, on purpose, take different paths so that at least I know which day of the week it is, right? Otherwise, we lose track of it, right? So to have a meaningful, enjoyable work-life balance, my advice to new students that are joining or whoever watches this video is to make friends. If you have more friends, you would have a really colorful life, and have diverse friends from everywhere.
Great advice.
Yeah, sure.
Thank you so much for taking time, and I really enjoyed this, and it was great to be back after so many years.
No, thank you for coming, Erdem. This was a very nice thing that the society has established and is doing. I hope that you can continue, and you will continue, I hope.
Okay, we would like to thank Dr. Sarabandi one more time. Thank you so much for tuning in. This is a wrap. Until next time, stay happy, stay healthy.